name is Ara Erfan, and this is going to be my project for 2CM4 on simulation inverse modeling of gravitational lensing using ray tracing optimization. So, modern telescopes like JWST capture incredibly detailed images of gravitational lensing, but these images don't directly tell me what caused the lensing. They only show how light has been distorted. So the key question I'm asking is, can I go from those observed light patterns back to the underlying physical system? In practice, you wouldn't observe mass or gravitational fields directly. What you actually measure is light, specifically how it arrives at a detector. So the only data available to me is this detector distribution, and everything I want to infer has to come from that. From this detector data, we want to recover the underlying system. That includes parameters like mass, strength, position, and even the number of sources. The difficulty is that different parameter configurations can produce very similar detector patterns, so the problem is inherently ambiguous. We can now state the problem explicitly. Given a detector distribution, we want to reconstruct the unknown system parameters, such that our simulated output matches what we observe. This is a nonlinear system with no closed form inverse and is limited observable data. So solving this requires a computational approach. We could formalize this as a mapping problem. In the forward model, we take known parameters and simulate the detector output. But in reality, we're solving the inverse problem, recovering those parameters from the output. And this inversion is highly sensitive and nonlinear, which makes it difficult to solve. In practice, this is computation expensive. In practice, solving this directly is extremely computationally expensive, and existing approaches rely on full relativistic simulations or large-scale data fitting. These messages are powerful, but they are not efficient for exploring parameter spaces or running optimization. So instead of full relativity, we use a reduced pre-existing model based on geometric optics. That model gives us a basic framework to map gravity to an effective refractive index, which allows us to model gravitational lensing efficiently by approximating it as a spatially varying refractive index. This sacrifices some realism, but it captures the dominant behavior while making the system computationally traceable. The key advantage is that this makes the system fast and flexible enough to support optimization and parameter reconstruction. So we represent the system as a pipeline, a source emitting rays, a field that alters the trajectories, and a detector that records the result. This defines a complete mapping from parameters to observable data. And once we have this mapping, we can begin solving the inverse problem. So in the inverse problem, we begin with a full 3D gravitational lensing model, treating each mass cluster as an individual point source. By comparing rays interacting with clusters versus no clusters, we verified that the physics of light bending was captured correctly, and this gives us a physically accurate forward model, but not yet something suitable for inversion. And here is how I changed it with regards to the release features being conical and constructing multiple point sources. And here's stop motion of the results. So if we zoom in, you can see that on the inside of the bending one, or the one near the masses, you can see how the light is bending and intersecting with itself. And so the 3D model provides a strong visual proof of concept, capturing how rays bend in gravitational field. However, for this application, it is overkill. The system becomes visually noisy, difficult to interpret, and hard to configure during parameter exploration. Scaling is also required to make effects visible, which complicates numerical behavior. So while physically valid, it is not suitable for efficient optimization. Without scaling, lensing effects were too small to observe in a limited domain. With aggressive scaling, the system became chaotic and physically unrealistic. This showed that a simply controlled model was necessary to balance visibility and stability. So at that point, I made a key design decision to reduce the system to 2D. This sacrifices some physical realism but significantly improves stability, and more importantly, it makes the system usable for optimization. So here's the initial setup. It's essentially the same steps but in 2 dimensions. And so here in this setup, you can see how we mapped the lensing analog and how it's bending with respect to the gravitational fields that we're simulating. And so we transitioned to a 2D model with parameterized gravitational sources, a control emitter, and a detector. This allowed us to isolate key behaviors like deflection and clustering of rays. Most importantly, this setup is simple enough to enable optimization while still capturing the underlying physics. So here's the setup with the freezing the rays that hit the detector detector and pointing the source to the detector. Um, so this gives us a stable and fully parameterized forward model, and this is the model we use for solving the inverse model. And you could see the final version of how light is bending through multiple gravitational fields. And more importantly, comparison, how gravitational lensing works versus no lensing. And it's like analogous to a real lens, but also analogous to how gravitational lensing actually works. Um, so these assumptions that we have listed here can reduce physical realism, but preserve the dominant behavior of lensing while making the system computationally efficient. Up to this point, the forward model simulates detector outputs from known inputs. In practice, those parameters are unknown. The problem becomes how can detector data be used to recover the system that produced it? The initial approach discretizes the detector into bins and counts ray hits. The simulated distribution is then matched to observed data through optimization. Conceptually simple, but it's unstable in practice. Here are the parameters. Here's the steps we took to set up the geometries by putting individual bins onto each tenth of the detector um, as ray detector BCs. And here is the objective functioning where we mapped we used a closed loop by using the withsol command, where withsol refers to our forward model solution. And then we use the WS get the ray detections on that bin and compare to the target, and we took a weighted sum and made that our objective function for comp solve to minimize. And so this method does work in similar cases. We were able to recover a parameter with about 7% error. However, once we introduced multiple parameters, the solver became unstable because it becomes highly sensitive to discretization and fails to converge reliably. So the issue arises from using discrete ray counts. Small parameters produce sudden jumps in output rather than smooth variation. This creates a non-smooth objective function. Without a usable gradient, the optimizer cannot converge. Key breakthrough was changing the data representation. Instead of discrete ray counts, a continuous density field is constructed over the detector. This produces smooth responses to parameter changes. The optimization problem becomes stable and solvable. Here are the parameters again, but for our advanced model, and it's a lot more because, yeah, with the variables too, there's a lot more. The important ones are the simulated statistics and the target statistics, because those are the ones that are being compared. Phi compares the error, and then our JUniv is our objective function with those weightings in the parameters. And so this slide summarizes how the full closed loop framework works. We run the forward model, extract physically meaningful features from the detector, and compare them to target distribution. The difference is captured through a weighted objective function, which is the optimizer uses to update parameters. The key is that we weight features based on how strongly they relate to parameters, emphasizing stable monotonic relationships. This allows the optimization to converge reliably even in multi-parameter cases. So here in the optimization methodology, you pick the parameters you want to vary. Here it's the positioning of the light source in the x and y. Then you run a parameter sweep over those x and y positions, all the combinations, and you identify the key trends that are held constant across different variations of those parameters. Here it's the skew versus the y data, even when x is being held constant. And then you adjust the weightings accordingly. So here we adjusted skew to be the highest because that was the one with the most consistent relationship. Then you run the solver over your unknown bounds, and then you get convergence, which it ended up being within 5% over two unknowns, which is impressive since the data was inconsistent, and we're working with two unknowns and two variations of parameters, which exponentially increases our and makes the regions much more harder to converge on. And so for another case study where we're only varying alpha, here we see that as we increase alpha, the concentration and total amount of rays hit go down. And the only variable that has a stable relationship throughout alpha is the total, because all of the other ones rely on convergence or symmetry. And as you can see, has a perfectly monotonically decreasing relationship. So what we do is we just set all the other variables to 0 since they don't really give us any information. And then we run our solver, and guess what? We get perfect convergence because the minimum of our results is going to be the local minimum as well. As you can see from this graph here, the minimum here is literally where our results is. And yeah, you see 100% convergence. We literally did COMSOL's job for him. And so there are several clear directions to extend this framework. First, we can scale the model back to full 3D and more complex multi-source systems. Second, we can improve the physical fidelity by incorporating wave optics and wavelength-dependent behavior in general relativity, and geodesics, which was what I was going to do originally. And from an optimization standpoint, one of the biggest improvements would be replacing manual weighting and decision-making with machine learning, allowing the system to automatically identify the most informative features and learn how to optimize those decisions over time. And finally, using multiple detectors such as distributed telescopes or satellite arrays would significantly improve reconstruction accuracy and distribution statistics. And in this project, we developed a complete forward and inverse modeling framework for gravitational lensing. The key contribution was transforming the problem from a discrete formulation into a continuous one, which makes optimization stable and scalable. This allows us to reliably reconstruct system parameters directly from detector data. More broadly, this approach enables fast, simulation-driven exploration of gravitational systems, which is essential when working within incomplete or uncertain observation, and that's what makes this framework both practical and extensible. Ultimately, this turns gravitational lensing from a purely observational problem into a computationally solvable one. So in practical terms, this framework enables rapid reconstruction of gravitational systems directly from detector data, and this makes it possible to test different physical configurations quickly, especially when working with incomplete or uncertain observations. Because the model is computationally efficient, it supports iterative exploration, something that is difficult with full-scale simulations, and this makes it practically useful for interpreting telescope data and validating astrophysical models. Thank you for listening.